Okay. So, Olivier, Malinur is a geologist with 33 years experience in the oil and gas upstream with a focus in West Africa. He's the founder of Welcome Energy Services, which represents for Africa Newmark Corporation, Chinese leader of LF-NMR analyzers with more than 800 installed analyzers worldwide. So please, everyone, join me in welcoming our speaker for today, Olivia. Olivia, over to you, please. Olivia, you're muted, please.
Let me unmute.
Okay, good.
Morning, everybody. So we are going to make this presentation as nice as possible and as fruitful for everyone. I want also to speak about the low field NMR for cores and cutting analysis. And I consider it like the best hidden secret in rock analysis. Why? Because usually people talk about CCA, conventional special core analysis. They talk maybe sometimes about CT scan, but rarely they use NMR. One of the best proof is that on the west coast of Africa, if you go from Morocco up to Namibia, to my knowledge, there is no frequency NMR analyzer existing. All right, so go first to an introduction. There is a proverb from a citation from a quote from Arthur C. Clarke, which is a science fiction writer, who say any sufficiently advanced technology is indistinguishable from magic. And what we're going to see is NMR truly, sometimes it's like magic. It's give us some information that are really, we say, oh my God, that's so nice. I was not thinking I could get that. So we are going to go through basic principle of NMR. I will make an introduction on the theory. Then we will look at the practical application in petrophysical. And then we will look for case studies. The first one being standard case, just simple NMR standard case. One will be HPHT, very nice with imaging and a lot of things, very interesting things. So let's start with a bit with humorous things. I had an interview of Mr. Randy March, which is the geologist in South Park. And I asked him, and he said, just leave that to petrophysicists and doctors. So that's wrong. We will see why. Why not use NMR for my special core analysis? I have run NMR loads, so there is no need for NMR. It's double wrong. What of NMR for mudlogging? And that one is a killer. Why not give T-bone steak to a dog? Mudlogging, wow, NMR. What is the quality of NMR result? I heard the permeability and the saturation from NMR are approximate. No, they are not approximate. We will see why. And MRI on core, imaging through magnetic resonance on core.
Yeah, are you there? Can you hear him, please?
Yeah, I can't hear him. I guess the network was from Zen. The issue is
Okay,
from
he
Zen.
said
I can't.
it. Put it up while he can voice over.
Okay.
Thank you. From our back soon. So, Olivier, are you there? Okay. I think this will be stopped. Let's just be patient and wait for him to come back up so he can voice over. Hello, Olivier, can you hear me? Okay, so before network always festival. Okay, for those of us in the meeting where you're welcome. The webinar for today is titled The Best Hidden Secret in Rock Analysis, and our facilitator for today is Olivier Malinur. So he had a bit of network challenge, so he'll join us shortly. So please let's be patient. Apologies for any inconveniences. So Olivia is back up. We're very sorry, everyone, for that breaking transmission. It was a bit of a technical issue. Apologies. So Olivia,
Yeah, problem. Okay, so we have finished the interview of this Mr. Randy March. When we ask for imaging resonance magnetic MRI on cores, he's just saying, why not using CT scan? So the answer is, why do doctors use CT scan and MRI? So the basic principle of MRI, number one, it's a very comprehensive technology. It's a technology that can be used for bioscience, that can be used for petroleum, that can be used for porous materials, that can be used for polymer like rubbers, and that can be used also for food and agriculture. It can be used as well for nanomaterial, painting, etc., etc. It has a lot of application. And we are going to focus on petroleum applications, okay? But first of all, what this MRI do? What NMR is doing? What is this nuclear magnetic? The first aim of nuclear magnetic resonance is to use nano perspective to explain macro phenomena. So we are going to try to understand the porosity structure, the permeability, the saturation, the movable and bond fluids, based simply on the nucleus of hydrogen. So we are going to measure the magnetic property of the nucleus of hydrogen. And the nucleus of hydrogen is made of one single particle, a proton, which is a particle charged positively. Okay? So this is why it's starting by N, like nuclear. Second, we are going to look at the magnetic property, which means that in the hardware, we are going to have a permanent magnet, we are going to have a radio frequency system, and we are going to have a spectrometer. Okay, this is the magnetic, the M of N. Is because we are going to try to put these protons in resonance frequency. We are going to see how. And for that, we need a software to modulate a pulse, correct pulse sequence. Okay, a radio wave. So now I'm going to try to explain you, and I will explain, I'm sure you will understand at the end of this presentation, what is a proton spin, why we say magnetic, why do we say resonance, what is a relaxation, and what are these famous T1 and T2 you see everywhere. You have to keep in mind that the most important things is that NMR is going to use radio spectrum electromagnetic wave, okay? Let's say going between 2 megahertz up to 100 megahertz. When you use a high field NMR, it can go up to, let's say, 1 gigahertz plus. Okay, low field NMR is lower frequency. And while the other method for investigating rocks, usually they use infrared, they use visible light. We use ultraviolet, we use X-ray, we use gamma ray. So it's two different, we are in two parts of the spectrum of electromagnetic waves, and it's given us a lot of advantage using the radio waves. So let's go for a video to explain the basic principle, the theory of NMR. So this is a proton, okay? In its original state, each proton is like a small magnet that is oriented. You see the north with the pointing arrow and the south in the opposite direction. And this turning randomly like this. Now, what's going to happen if we put a magnetic field, if we put a magnet, very strong magnet, we are going to have proton orientating either in the direction, on the opposite direction of the magnetic field, okay? Those who are orientating in the opposite of a magnetic field, it's because there is an increase of regional energy, like a heat or something like this locally. Those who are orientating in the direction of the magnetic field, it's because it's a low energy they're in low energy states. Okay? In truth, they are not rotating on themselves like this. They are rotating a little bit like the Earth around the sun. There is a precession. Okay? There is an angle of precession and there is a frequency of precession. And this frequency of precession is directly proportional to the strength of the magnetic field. So if we put a strength of 1 Tesla, the frequency is 42.58 megahertz. 2 Tesla, it's going to be 86.16 megahertz. 3 Tesla, 127. So basically it's 42.58 megahertz per Tesla. All right, not very complicated until now. Now let's take all these protons and imagine we are putting all of them to a same common origin. Okay, so what is it going to give us? We are going to have something like this, with the majority of the proton having magnetic, they are oriented upward, and a minority being the high energy proton with the north oriented downward. Okay, so this is the way it is. So now, if we make the sum of the magnetic moment, it's going to point upward. You agree with me? These things, first key concept is called longitudinal magnetization. This is the famous longitudinal magnet. All right? Now, if we apply a radio wave to this hydrogen that are inside magnetic field, let's apply a radio wave of the same frequency, resonant frequency, with basically the frequency of the precession. Okay? So, oops, what's happening? Okay. If we apply a radio wave to this hydrogen inside a 1 Tesla field, for example, what we are going to have, we are going to have two phenomena that will be happening. The first one, that the proton will absorb energy in a high energy state. Okay, so they will go downward. Okay. So when we have this, we will try to apply so that 50% will point upward, 50% will point downward. And the longitudinal magnetization, it appears. All right? Now, what's going to happen as also when we apply a radio wave is that our protons are going to enter in resonance. It means they are going to have the same phase for rotation. And this will now create a net magnetization moment, which will be orthogonal to the original longitudinal magnetization. All right? So this net magnetization, this transverse magnetization that we have created can be measured simply by using a coil. And you know the experiment, we put a coil, we put a magnet inside a coil, blah, blah, and it's generating a current, okay? So this is very simple theory, but this is how we're going to measure this transverse magnetization, okay? Now, imagine we are stopping the radio wave. The first things that will happen is that our protons, which are all of them charged positively, they will push themselves back and we will lose this transverse magnetization. Okay? So we stop now the radio wave. The protons, they push themselves back and we lose the transverse magnetization. That's the first phenomenon that will happen. Okay? The duration from the time we stop this radio wave till the time we get zero, we lose the transverse magnetization is called the T2. That's the T2, and it's what we are going to use the most. And then the proton will go back to their original states, okay? And will release some radio wave, and we will regain the longitudinal magnetization. This is what we call the T1. So when T1 happens, it's releasing some energy, and it's called also spin lattice relaxation. Okay, this is the T1 relaxation or spin lattice relaxation. So that said, we can go now. So to summarize, T1 reflects the length of time it takes for regrowth of longitudinal magnetization back toward its initial maximum value, and T2 reflects the length of time it takes for the magnetic resonance signal to decay in the transverse plane. Okay, that's not so complicated. Now I told you about low field NMR and high field NMR. Why high field and low field? It's basically the medical equipment. It's magnets that have a very strong magnet, superior to 1 Tesla, for enhancing image quality of human body. It's a superconducting magnet. The weight is tons and tons. It's heavy, it's expensive, and it's very high maintenance cost. For our analysis, we are using low field NMR, which is less than 1 Tesla magnet. It's less affected by ferromagnetic material. And we know that there is ferromagnetic material inside our rock, like pyrite, like limonite, etc. It's a permanent magnet, so there is no maintenance cost. It's low weight, it's portable and inexpensive. So, for example, this set here is about 80 kg. Okay, so the low field NMR is more suitable for porous media analysis, basically rocks, reservoir rock. So now let's go to the application in petrophysics. The first application quickly is the porosity. Determination of porosity is almost instantly. So when you have your NMR signal, the NMR signal intensity is proportional to the volume of hydrogen containing fluid under the same measurement conditions. So basically, the amplitude of your signal will give you the porosity of the rock. The second is the porosity distribution. So the T2 relaxation time is proportional to the pore radius. So for a given pore, with a given radius, you will have a given relaxation time. Okay, so you can convert the spectrum of the T2 inside into a pore size distribution curve. So you will have straight ahead your pore distribution curve. Your porosity histogram. It's a little bit of very simple physics. The T2, the inverse of T2, is equal to the inverse of T2 bulk. This here, which is the pore component, which we call the surface relaxation, and here, which we call the diffusion-induced relaxation. Okay, the bulk relaxation depends on the viscosity and the chemical composition of the liquid. Okay, the surface relaxation depends on the surface of the pore, volume of the pore. So if you divide the surface by the volume, if you imagine the pore is a sphere, ideally, you will have a radius. So it depends directly on the radius of the pore. And the diffusion, we are going to talk about it. It depends, it's the diffusion of the liquid itself through the pore, and we're going to talk about it later on. But we can approximate that the reverse of T2 is equal to that. So basically, the reverse of T2 is proportional to the radius of the pore. Okay, so if we have a big pore size, we are going to have a slow decay time. Okay, and we are going to have our T2. If we have a medium pore size, we are going to have a T2 there. If we have a small pore size, our T2 will be there. And at the end, we're going to have the spectrum, something like this. Okay, so practically what we do, we get the original data. This is the original data. Okay, so it's the time versus amplitude. Then a Fourier transformation, and we are going to get the different peak of the T2, and then we can transform this curve inside a pore size distribution that we have here. So here you have different bins with diameter of your pores. You have directly your porosity curve. And just remember the principle of this, it's not affected by the mud cake, or it's not affected by anything. It's giving you straight ahead the pore size. The second things you will get, the third information you will get, very important, the movable and the bound fluids. So basically, under a certain diameter of pore, certain radius of a pore, the fluid will not be movable. Okay, so the movable fluid depends on the diameter of the pore, on the pore radius. Okay, so as long as this pore radius depends on the spectrum of your T2, we can put a cutoff. Under this value of the T2 cutoff, we're going to have bound fluid and the clay bound fluids. And above this T2 cutoff, we are going to have free fluid. Okay? So it's very important to determine this. And for that, what we are going to do is we will take our sample. Sorry, I will explain it a little bit more in detail later on, but we will take our sample, we will centrifuge our sample, and we will measure the sample remaining. And this sample that we have centrifuged contain only the water, or the fluid from the water of the fluid that is bound to the rock. Okay, that is not movable, that is not free. So why is it important to do this? It's important to do this because when you use logging tools, they have fixed cutoff for the T2. They say it's 33 milliseconds for sandstone, 92 milliseconds for limestone, 3 milliseconds for clay, etc., etc. But when you do core cutting analysis with NMR, you will discover that this cutoff is completely off. It's not corresponding at all. And very often, you end up with a change in your recovery factor, because the bound fluids and the free fluids will give you later on, ultimately, your recovery factor. Okay? So it's very important to determine the T2 cutoff. Fourth information we are going to have is the permeability. The permeability depends on the movable fluids inside the core, and there are two equations to do this. The first one is the Coates model, which is valid for very supple and very easy to use equation, depending on the porosity, the free fluid, and the bound fluid. The second is the SDR model, Schlumberger-Doll Research Center model. It's valid only for water reservoir. However, it works in some cases very, very nicely for gas reservoirs, sometimes when you have on gas but it's more for hydrocarbons. Generally, people use the Coates model. They prefer to use the Coates model. It's giving a better result. So you remember we have the porosity, we have the free fluid, we have the bound fluids, and calculate the permeability. The get is the characterization of the fluid. We're able, through the graph from the diffusion and the T2, to find which type of fluid we have. So remember, we have the diffusion here, which is this term, and we have here the T2, the total T2, okay, which is this term here. So if we plot this versus that, okay, you have one line here, which is purely depending on the T2, which is going to give us the bound water or the water, okay? And this line is depending also only on, for finding the bound water and the free water, it's depending on the T2, and to find the line separating purely on the diffusion, okay? So here for the water, here for the gas, and here you have the line of the liquid hydrocarbon, the oil. So when you go down toward the southwest, you get heavy oil, and when you go toward the northeast, you get light oil. And when you move toward the northwest, you get an increase in GOR, okay? This is an example here. So you have the line of the oil, okay? And this place is the oil peak, and here we have a water peak. Okay, so we can characterize which type of fluid we have inside inside a rock. 6.1, and we are getting to something more and more interesting. It's the imaging. We can do imaging. So when we do the classic things that I've been explaining you so far, we are sending a signal and we are imaging the whole object, okay? And we are getting an information on the whole of this lemon. What if we were able to send for each voxel in this lemon, it means each 3D pixel in this lemon, on an image of, let's say, 1024 by 1024 or 256 by 256, what if we were able to send a signal that is different for each of them? If we were able to code this signal so that each voxel will have a different code, a different information. So this is our sample. Our sample is inside a magnetic field, and you see we have all the spin which are aligned like this. Now, if we simulate the magnetic field, if we put the magnetic field, let's say 1.2 Tesla on top and 0.8 Tesla at the bottom, we will at the same time then we send the pulse, knowing that the pulse has the radio pulse has a certain frequency, we will be able to excite only the place where the magnetic field is equal to 1 Tesla. Okay, you follow me? So what we will have done, we will have selected a layer in the core. So initially on one layer, we have only core, we have achieved resonance, and we have all our hydrogen in the same having the same frequency here. Now, what we are going to do is that we are going to send a pulse. We are going to do the same things, but in the x-axis. So you will see that in the x-axis now, we are going to have a shift in the phase of each or voxel. in the y-axis, that means that now in the y-axis, we will have a shift of everyone. So every single voxel now has a different signal, okay? And we can measure each voxel and get the plus X, Y, Z plus the attribute, the T1, the T2, etc. Okay? So it gives us beautiful things. It gives us, let me move that things. This is a shell, a source rock, okay? Usually it's a oil shell. And we have different slices, 1, 2, 3, 4, 5, that have been determined, okay? And we can observe at the same times in black and white, the cracks inside the rock. But not only that, because that things, we can get it with CT scan, but here we can see the places where we have kerosene. You see, these places there, this is the place where there is kerosene and where there is oil, okay? So we see directly, we have information on saturation directly on the rock, without cutting the rock, without doing anything. You will see straight ahead the information. That's magic, like I said at the beginning. You are able to understand what's happening in the... So how do we do basic analysis? We have two cases. Either we have a rock without hydrocarbon or we have a rock with hydrocarbon. If we have a rock without hydrocarbon, the first things, if you want to follow the procedure, you will have to leave the core for 8 to 24 hours under vacuum pressure inside distilled water, so that the rock will be 100% saturated. Because when you remove the rock from the earth, the rock will be, there will be flushing and so on. So there will be places where there is no fluid inside the rock, and we will not be able to analyze everything. So let's saturate the whole rock under distilled water. So the whole rock will be saturated in distilled water, and we will measure the porosity and the pore size distribution. The next step will be to centrifuge the sample. Okay, so once we centrifuge the sample, we already have the porosity, the pore size distribution. Then we measure the centrifuge sample, and when we measure the centrifuge sample, the only water remaining will be the water which will be under the T2 cutoff, and we will be able to measure the T2 cutoff. We will be able to measure the T1 cutoff if we want. We will be able to have the free fluid, the amount of free fluid and the amount of bound water, and we will be able to calculate permeability. As simple as that. Now, let's see what's happening if we have a sample with hydrocarbon. If we have a sample with hydrocarbon, first thing, well, these different steps, you know them, it's what I just explained. Now, there is an additional step, is that you are going to take your sample and you will leave your sample inside manganese chlorine. What's happening with manganese chlorine? Manganese chlorine will decrease the, it will decrease the water signal, the T2 water signal. Okay, it will decrease it and make it disappear after a while. So the only signal that will appear will be the oil. So in that case, you will be able to have the original saturation and the saturation of oil, the saturation of water, in addition to the other information you are getting. All right. So the sequence of measure is basically get the porosity, the pore size distribution, the BVY, FFI, T2 cutoff through centrifuge. Later on to LT, the formula. If you have a sample with oil, you will get saturation of oil, saturation of water. You can use for that two possibilities. You can use a diffusion plot, diffusion T2 plot, or you can use also chlorine, manganese chlorine soak sample. Then you can do some imaging. And remember, in imaging, you can look at the parameter like saturation, etc., based on local slice. And you can do HPHT study that we will look later on. For those who say about the approximative value of porosity or BVI, etc., using NMR, here are numbers. I ask my people in from NUMAC to make a measure. So they made measure on different samples. And this is the porosity using classic weighting method. And here is the NMR. This is the curve between the two. You see the curve between the two is almost perfect. It's giving a perfect result. And I've not done it for, this is a centrifugal volume of water. Okay, so basically the BVI. So this is, if you use the methods by weighting, and if you use the method by NMR. So you see the results are almost the same. If we make a comparison between NMR core analysis, logs, and classic core analysis, NMR core analysis, you can analyze the whole core. For the logs, the depth of investigation is about 4 inches. Maybe it has changed, but so far I know it's 1 to 4 inches. It's pretty shallow. For classic core analysis, whole core. Sampling, the sampling rate is discrete for NMR core analysis and for classic core analysis, while for logs, that the big advantage is continuous. Imaging, you can do imaging with logs, with NMR logs, with NMR core analysis, but not with a classic core analysis unless you use a CT scan, which is not going to give you the same things. Reagent, apart from the MnCl2, chlorine of manganese, we don't use reagent. Same thing for the logs, and you use many reagents in classic core analysis. Environmental impact, there is no environmental impact, both for both NMR methods. For classic core analysis, there is mercury, organic agent, CT scan is a radioactive item, so there is some precaution to take. The ease of measure, NMR core analysis is extremely simple. Logs is pretty tough to put in place, to say the least. Classic core analysis, for those who have used the once Soxlet, they will understand the pain, and it's not always easy. For the ease of the interpretation, it's very easy to use with the NMR core analysis. Logs is the same, it's pretty easy, and core is also pretty easy. Now, the big advantage of the NMR core analysis is very fast. Logs is slow, and classic core analysis is low. The cost of NMR core analysis is average, high, and for the logs and for the core, classic core analysis is low, except if you start to use a CT scan. So these are examples of instrument analyzer. So you have here the micro, for example, for which go from 2 to 23 megahertz. Okay, usually 12 megahertz is largely for analysis, at least in Nigeria, because we don't have unconventional. 23 megahertz is for unconventional rocks like shale, you want to analyze shales of these things. The sample go from 1 inch to here, the macro up to 6 inch. We can go from room temperature and room pressure to HPHT analysis with 10,000 PSI and 120 degree. My colleague told me even we can push up to 150 degree. We can do only a relaxation measurement, but we can do with the meso here and the macro. We can go imaging and relaxation. And we do also flooding experiment with the meso and the macro, gas, flooding, liquid, polymer, etc. Okay, so this of the small micro. Okay, So this whole system is about 80 kg. This is what we call the probe. It's 1 inch core plug inside it, and you're going to measure your porosity distribution, etc., etc. Okay, you have a mouse, keyboard, and you have here your radio frequency system, spectrum system, computer link. So what is interesting you now, we understand a little bit what are these T1, T2, and so on and so on. We can look at case studies. So here we have a sandstone, and we are, it's a very simple case. We are analyzing this sandstone. So you see the blue spectrum there. This is the original spectrum for the T2. This is here when we saturated with water. And this is when we use manganese chlorine. So the difference between this and this is the water, okay? So at the end, we were able to calculate our porosity, 15.2%, bond fluid saturation, 45.85, free fluid, 54.15. The oil saturation was 25%, and the water saturation was 87.5%. Not very interesting sample. Here is another example. Here we look at the T2 spectrum, and this is translated in the pore throat distribution histogram. And we have the T2 spectrum, and here we have the pore throat distribution. Straight ahead, this is the pore radius. You have a pore radius straight ahead. That's fantastic. You know, for, let's say, for sand control, for example, this is basically what these guys are looking. We are talking about sand control, so let's stay with the driller. That one is interesting. We have two slurry cement. Okay, so we have a slurry where we put 50% water, and what we see, this is after 1 day, we have here a peak inside our T2, while with the 50% water, we have two peaks. Because imagine your cement is water with particle of cement inside and some bubble, okay? And inside this bubble, you have water. This is the free water here that is inside the bubble, and this is the water that is with the flocculant. So here you have the water with the flocculant, okay? And the more we are going to wait, the more this free water will disappear, the 50%, until after 28 days, we still have a little bit of free water there, but we can see that the time is between, let's say, 0.1 milliseconds and 1 milliseconds. And here we see the time is also 0.1 to a little bit less than 1 second. Okay, so we got almost the same spectrum after 28 days, but it took time. It took longer time to dry, which we understood with 50% water. But we can make experiments like this, quite interesting for cement. Look at the curing time of cement. Look at the optimal percentage of water, etc., etc. Using a diffusion diagram, so we have our diffusion here, and we have our T2 here, and we have a sample where we have gas that you see here, we have water here, and we have oil here. And based on the age of the peak of oil, gas, and water, we were able to determine the gas saturation is 10%, the oil saturation is 40%, and the water saturation is 50%. Here, we are having a little bit more complicated case. Definitely, we have water here, we have gas here, but what is these things? These things here actually is condensate. Okay, so we have a very light oil or condensate, which is just located at this place. Okay. Now we are starting to have our cores images. So this is a core image. You see our core. So we have a transverse image and we have a coronal image. And when you look at the saturation basically of the core, you see where the hydrocarbons are located inside the core. So you can see very well where the hydrocarbons are located inside the core. You see that inside this crack here, there is a fracture there. There is no hydrocarbon, okay? But you see the places, the patches, hydrocarbon. This is quite interesting image. That's an example with mudlogging. So forget a little bit everything I've said about video. When you are mudlogging, the cuttings are so small that you don't really need to put them inside vacuum for 8 hours. You can take your cutting, you wash your cuttings, and you can make the analysis directly from the cutting, okay? So when you have cuttings, here you have the chromatograph, you have your methane, ethane, C3 and C4, propane and butane. And they found that there was probably some oil layer. So here we are measuring the total peak area, the left peak area and the right peak area. And we have determined a coefficient from the NMR that help us to find whether it's an oil zone or a water zone. And we were able to see that what NMR found, the place where we found that there is an oil zone, correspond to exactly the same place what our gas found. So it's a very good correlation between the oil content and the gas measurement to find the oil layer. It's a very I started my career as a mudlogger, and I can tell you, if we had this type of measurement, it would have been fantastic because it can give you very, very, very precious information. It can give you, in addition of giving you the oil, you will have directly the porosity, a real value of the porosity, and you can calibrate the real value of porosity. Look at the value that people from LWD are doing as well. So it's a very interesting method. Which is basically what you are, I'm supposed to be awaiting all of you. So HPHT, this is an example of a setup at a client's office of an HPHT system. We have here the NMR and MRI measuring systems. So you put your core here. You have the HPHT flooding system. So the things that going to, the device that's going to control the injection of the fluids inside the core. And these are the core holders. So this is critical. The core holders are the things that going to be able to support the pressure and be able to, they must not disturb the measurement. Installation in other places, okay, for HPHT system. Okay. So at the beginning, you have a core holder that's going to hold the core, isolate the confining fluid, and input also the flooding medium inside the core. So you have a confining fluid, which is fluorine oil. It's a special of oil. The temperature is going 110. Let's say I put 110 for a reason like this, but it can go up to 120, 150 degree. The maximum temperature is 70 megapascal, 700 bars, largely enough for doing our experiment in Nigeria. Then here you have the gas flooding system or a liquid flooding system. So you inject your water or your gas or whatever inside your core, and then control system to control the pore pressure inside your core. Okay. So then you have the NMR and MRI measuring system to measure the hole. Now, the core holder itself is made a non-metallic material because else the NMR will not work if it works. It has a very low NMR background system. It's working at high pressure and high temperature. It's a mixture of fiberglass, colophane, and what we call PEEK, which is polyethylene ethyl ketone. It's a special material. The core itself is wrapped in the HPHT system. It's controlling the pressure and the temperature. And then we have to ensure that there is no disturbance. There is an electromagnetic compatibility for all the rest, for all the system, so that there will not be disturbance for the radio wave and so on. So first case, we have here a nice sandstone reservoir like we are used to, and decided to create 3 slices. So we can visualize many slices at the same time. Okay. For example, here we have 3 sagittal slices. Okay, each slice is separated with 7 millimeters. Okay, and we are going the average information inside this slice. Okay. We are injecting water inside a core sample where with oil, saturated with oil. Okay, so we have first saturated the core sample with 100% oil. Okay, and we start to inject, and we are going to inject up to 1 pore volumes. So if your core is having a volume of let's say 100 cc, and the porosity is 20%, we're going to inject 20 cc of water progressively. And you see at the beginning how it's working with 10%. 10%, I will answer the question later on. 10% of the pore volumes, here 20%, and you see the progression of the waterfront until here we arrive at 1 pore volume, and the saturated oil stay at 33%. On the second slice, we have exactly the same, almost the same image. And when we arrive to 1 pore volume, we get 32.9%. So it means that at the end, the residual saturation of oil will stay at 33%. Okay. Still the same. Here, we can see for the 3 slices, the saturation 0, 5, and 1. We can observe this also on curve if we want. And we can look at the result. So this one is using NMR, and this is the result using a metric classic method, okay, non-NMR method. So first things you have to remember is that NMR is measuring the number of fluid, the amount of fluid you have inside your core, while the traditional methods measure the amount of fluid that is going out of the core. Okay, so the traditional methods are usually very slow, while for the measurement, while the NMR is pretty slow, it's pretty fast. And you can look at the progression of your waterfront on different slices. Okay, in this case, it was a clean core, so it was a very homogeneous sandstone, so it's not very interesting. There, I have a sandstone that is really non-homogeneous, okay? And you see the progression of the waterfront, the cone inside your core, progressing and reaching places where you still have to disappear. It's staying there. You see these patches of oil there. This is the residual oil. Okay, so this is an animation of what's happening. Okay, so and this is the on one place, and you see the places patches are remaining. Okay, so just playing animation a second time. Oh, this case here show us that at the end of the when we will have finished to inject this full pore volume inside the core, the saturation is staying around 41.6%. So residual, much more residual oil in that particular case than when we had the homogeneous sandstone. Now, imagine the application of this in water flooding with a laminated reservoir or heterogeneous reservoir like we have very often in Nigeria. It's okay. So you see immediately the application and the interest of for improving your recovery, the recovery. Okay. Here, case number 3 is the kind of opposites. We have water, and we look at the way the oil is going to percolate and to enter inside the core. So nothing is happening basically before 50 minutes, and then flow is happening, and it's going through the side of the core, passing there, and later on invading the other side of the core and leaving the center of the core like this. So the explanation I got was that it was due to insufficient annular pressure and low delta P between the annular and the core, okay, and the pore pressure. So I honestly, this is the, that's all. Here, this is a carbon capture and storage application. I know this is not yet in Nigeria, but don't worry, it will come one day or another, because there is a lot of fields that are abandoned, that are maybe, could be maybe very good permeability, good porosity. So what's happening there? We are doing an experiment under high pressure and high temperature to look at what's happening when we inject CO2 inside the reservoir. Okay, and you see the amount of water decreasing, the saturation of water decreasing on the core. And that one is very interesting. It's also carbon capture and storage. You have a carbonate core. Temperature is 5.5 megapascal, and sorry, pressure is 5.5 megapascal, and temperature is 25 degrees Celsius. So basically, it corresponds to something at 500 meters depth. And we inject this time water saturated with CO2 saturated water. And what we observe is that originally the porosity was 30%, and the permeability was 24.09%. Very fractured reservoir. And after that, the porosity has increased of 3%, which is an absolute 7.8%, 7.9%, almost 8% of increase of porosity. But the permeability has increased of 62.96%, almost 40 millidarcy. And you see the places where we have now better porosity, they are lighter color, lighter blue color. So let's go to the conclusion. The application of exploration and production for NMR, for core and cuttings what we are going to measure is basically the T1 and T2 relaxation, the diffusion. We're going to do imaging and HPHT flooding experiment. The parameter we will acquire, porosity, permeability, pore size distribution, DVI, FFI, of water saturation of water stability, capillary pressure, the grain density, the fluid type, and obviously, if we do the application is for, we can have application for water, gas, polymer, or chemical flooding, evaluation of reservoir formation, triaxial compression damage analysis to see if there is a decrease in the porosity under certain condition. Drilling fluid intrusion damage, physical property and curing of cement, conventional carbon capture and storage, unconventional reservoir, gas hydrate, and mudlogging. Okay, there might be other applications. So the big advantage, one measure, many parameters, the time gain. We move from hour to minutes, and the application is almost near time for cuttings, for example. We can do image repartition to visualize the fluid and the core, measure the parameter on the slice. The simplicity, the calibration is very simple, the measurement is very simple, interpretation is pretty simple. I will turn to geologist Randy Mark, and I think he's convinced now that NMR is the best. And I would like to add, for concluding here, a small modified, someone suggested me to put Yoruba. So I put this Yoruba proverb, which normally say the wise man, only the wise man knows the pregnancy of a snail, and I would say only the NMRs know the pregnancy of snails. So NMR is helping you to know almost invisible things, some things that is, as I said at the beginning, normally not attainable other than by magic, but here we use NMR. Thank you. And if you have any question now, I'm waiting for you.
Thank you very much, Olivier, for that enlightening session. Thank you. So I'm just going to go over a brief recap, and then please, if you have questions, post them in the comment section. I'll take them. So I'll look forward to your questions. In summary, the MRI is a very comprehensive technology, and it can be used in different industries: the petroleum industry, the petroleum industry, the health industry, basically to find pores. And NMR, which is nuclear magnetic resonance, is basically using nanoparticles to explain the macro properties of macro phenomenon, right? And then there are two types: the high frequency HF and the LF-NMR. And differences being that while the HF is heavy, is more expensive and has high maintenance, the LF is more friendly and is suitable for porous materials. So there are different applications for the LF-NMR, such as in determining permeability, fluid characterization through diffusion principle, porosity distribution, pore size distribution, and imaging. It basically helps us understand what's happening in the rock without cutting through the rock. And then you went ahead to show us its comparisons with other classic measurements, and then it was almost the curve. The result showed an almost perfect curve. And then in comparison with close and classic core analysis, it showed that unlike the others, you can investigate the whole core. You know, there's no reagent introduced into your core. It has very low environmental impact. It's easy to measure, easy to interpret, and it has fast speed in procuring results, and the cost is quite average. So thank you very much for this session.
Karen?
Okay. Yeah, go ahead, please.
I have a couple of questions that came privately. One from Mr. Alyunsek about the determination of the relative saturation of the fluids. Alyun, I will answer to you privately, but basically we can determine using these manganese chlorine methods or using the diffusion, the different saturation of the saturation of oil, the saturation of gas, and the saturation of water. However, the saturation of gas is pretty difficult because usually the gas is flushed out of the pore. How can NMR be used from Mr. Akinchete or Lakunle? How can NMR be used in hydrate formation briefly? Unfortunately, it will be another group of slides to share, but there is a possibility to. There have been a lot of studies on using the NMR and hydrate, because basically hydrate do not have an NMR signature, but when the hydrate is decomposing, the NMR signature is appearing, or when there is gas and water, you will not see hydrate. You will see the NMR signature, and when the hydrate is forming, the NMR signature disappear. Okay, so there is things that can be done, and how accurate and representative are using the mudlogging with NMR? Can the result be believed, especially where logging is tough? Yes, the results are pretty accurate for the porosity distribution. It can give some information on the saturation, but keep in mind that the cuttings, when they arrive at the surface, very often they are partially flushed of the fluids, especially if you have condensate or gas. Okay, so let's keep this in. Please, could you throw some light on comparison of permeability from NMR and VHP survey? Sorry, I don't have any information about this. I can ask. But so far, I don't have the information comparison with VHP surveys. What I can say is that the permeability of NMR obtained by logs, obtained by core analysis, correspond very closely to the permeability obtained in classic core analysis, conventional core analysis methods. Okay. Hello?
Okay. Olivier, have you taken all of the questions?
This is all the questions I've seen that were sent privately and unprivately.
Okay, so I think we have one more question and then we can call it a day. So the question says the LF-NMR has several applications. Can it also be used to indicate invaded zones or skin effects in the well bore and the reduced porosities in these areas?
Alors, I'm going to be clear about this. We are talking about NMR on core and cuttings. So we will not be able to look at the invasion zone, etc., etc. This is not going to give any information on that. We are looking at the core and we are looking at the cuttings once they are out of the hole.
Okay, noted. Thank you very much.
About the slides, they will. I will have to. I will send the slides to Karen, and she can send it to those who are interested.
Okay, so if you registered via mail for the webinar, a copy of the recording for the session and the slides will be shared to you. Olivier, please, can you put up the other slide for a minute? So thank you very much, Olivier, for this session. It has been really engaging, and I'm sure a lot of us that joined in learned a lot from it. Thank you, everyone, as well, for joining in this session today. Just a brief announcement. If you enjoyed the session today, You also want to stay tuned for our next session on the 3rd of October, titled Leveraging Business Analytics in the Oil and Gas Industry. And taking us is going to be Adionye Adafe Jaja. So this is the flyer. You might want to register. The link is there. Next slide, please. We also have another event on the 8th of October, and the title of that is Thriving with Emotional Resilience, and taking us is Dr. Osaz. So you also want to register for that as well. Next slide, please, audio. So I'll indulge all of us. If you're not following us on our social media platforms, follow us on, connect with us on all our social media platforms so you're aware of these activities. On LinkedIn, we are SPE Lagos Section 61. On Twitter, Instagram, Facebook, and YouTube, we are SPE Lagos. Connect with us, follow, share our posts to stay informed of all our activities. You know, we have a couple coming up and you don't want to miss out. Thank you once again, everyone, for joining us today. And I hope we all have a nice day. Thank you. Thank you very much. Thank you very much, Olivier.
Thank you, Karen. Bye-bye.
Bye.